Hello everybody, as I'm explaining new video for every new week. The video for this week, it is the I will explain the DENAVIT convention, which is the classical convention that everybody use in labeling when they try to do labeling for their robot manipulator kinematics. So I will use this principle in my kinematic analysis, and I publish one notebook when notes in my LinkedIn account, so that you can have a look at it. As you see, this is my 3D design. So I have 4 joint, this is the first joint, this is the second one, this is the third one, and this is the fourth one. And I have 2 gripper. This is the first gripper, and this is the second gripper, and this is my base frame and base length. I will mention in the second slide about how did I approach to my labeling and how did I use classical convention to abstract or to obtain the parameters that will control the DENAVIT label. This is the basic approach that I apply to my calculation. So as you see, we have the first frame and the second frame, and we are going in this direction. We are going in this direction. This we call it the previous frame, and this is the current frame. So OI, origin I minus 1, and origin I. So as you see, this is the XI, YI, ZI, and this is xi minus 1, yi minus 1, and zi minus 1. And we have 4 parameters. The first parameter is di, second one is ai, and the third one is alpha I, and the fourth one is the alpha theta I. 2 is translation, and 2 are rotation. So these parameters are controlling the DENAVIT labeling. So in order to do any kinematic analysis, you have to obtain these 4 parameters. How did we approach to these parameters? So that di, it is the distance, perpendicular distance between xi to the origin of the next joint, and it must be in along or a coincidence to zi minus 1. As you can see, this is the zi minus 1. So the direction of di is in the direction of zi minus 1. But ai, it is the perpendicular distance between the 2 origins, but it is in the direction or along the direction of xi. This is the xi, and ai, it is in the direction of xi and coincide to it. What about the rotations parameters? The first rotation parameters, which is in clockwise direction, alpha I, it is the rotation between zi minus 1 to the zi. If you can see, we can, for example, carry this coordination. This is the first coordination. We can see it. This is zi minus 1. And this is, for example, yi minus 1. And this is xi minus 1. We carry it to here. And if we rotate, this is zi to zi minus 1 to zi to here, we can call it alpha I. About the theta I, it is the rotation angle between the previous xi minus 1, this is the xi minus 1, to zi. If we carry this to xi, if we carry xi to here, you can see to here. So the rotation angle between xi minus 1 to xi, we can call it the theta I. And the name of theta I, it is joint parameter, and the name of alpha I, it's the name of link parameters. And also di, it is the joint parameter, and alpha I, it is the link parameter. They call it this like this in DENAVIT-HARTENBERG convention. I hope this is clear, and let us go to the next slide. This is the labeling. As you see from the previous slide, we have 4 joints. This is the first joint, this is the second joint, third joint, and fourth joint. As we can see, this is the axis. This is, for example, Z0, X0, and Y0. Why the Y-axis is not that important. The most important are X and Y, and DENAVIT-HARTENBERG is carried on it. For this one, for this is it is an offset. I suppose to be an offset. So because we don't have any revolute joint or prismatic joint, I suppose them to be fixed, and it is fixed parameters. So I take it into my consideration as offset. So I will add it after I do my kinematic analysis. I start from here. And to go on this first one, and then I label the axis Zi, Z1, and Z2, and Z4, Z3. So as you can see, the Z axis, it is in the direction of revolute joint. If you can put it in your right hand rule, so the Z direction is in the direction of revolute joint. This revolute joint is in up to it, and the direction of the third one, it is in revolute joint direction. And in here, this is it is a fixed axis. I don't have any revolute joint here, but I suppose it's because I carry the axis of DENAVIT-HARTENBERG. And the fourth one, it is also in the direction of revolute joint. This is the direction. I suppose it to be like that because we have to have arbitrary axis. So I suppose it in this direction to be symbol. And the fifth one, it is also in here. And then I label x-axis. X-axis, it must be perpendicular to the current z-axis and the previous z-axis. You can see this x-axis one, it must be perpendicular to here and also to here. And the third one also, x2, it must be perpendicular to z2 and also z1. You can see z2, it is in the direction of fy axis, and z1 is in the direction of z-axis, and it is the x-axis. It must be perpendicular to both of them, and we can go like that. When we come to the parameters, so you can see a1, it is perpendicular distance between z-axis and in the direction of the current x-axis. So it is x-axis, and a, it is in coincidence to x1. A2, it is in a coincidence of x1, x2, and also the perpendicular distance between z2 to z1. Also A3, it is the same. D4, you can see it is the perpendicular distance between x-axis and in the direction of the current z-axis too. And also the D4, because this one, we have two grippers, I label it as D4 E1 and A4 E2. Why I say this is A and this is this is D? Because it must be coincidence to X, so it is link parameter. It must be coincidence to Z, so it is joint parameter. So this is the labeling of DENAVIT-HARTENBERG parameters, and from here we can extract the label that we are looking for, starting from AI, alpha I, and DI, and theta I, and come to here, do the axis labeling. Link, we can see link I, 1, 2, 3, and go on. and it is easy to abstract your parameters, which are translation or rotation, and obtain your transformation matrices that you can use in kinematic analysis. I hope this video will be very helpful. I suffered and I face lots of difficulties to obtain these kinematic conventions because it is new kinematic shape. So it is not famous for lots of robotics, robot manipulators. It is new configurations. So I tried in my 3D, like a SolidWorks sketch, and the end effector come to my target position, and I tried with Python code. I get the same results. So this is labeling. It is correct. So you can try your own kinematic convention, and you can get the same result. Thank you so much, and have a good day. I hope that will be helpful for you, and don't forget to share the video with those who are interested with robotic calculations. Have a good day, and thank you so much.